In the next section, we'll look at the Knuth-Morse-Pratt algorithm, the same three names that popped up in the previous section by giving the key ideas to improve the construction of string matching automata. But the final solution that they came up with looks slightly different, and it gets away without this sigma factor in the space for the string matching automaton. So if you recall, the string matching automaton as a DFA was essentially as fast as it could get for the matching part. But it needs this transition table, which tells you for each state and symbol where to go. And it just seems impossible to reduce that further, because you need to specify where to go. But the simulation in the construction of the automaton looked very, very similar each time. We always had this error state X, and then we copied the entire column. That's already screams redundancy in your to you, that you're copying these entire columns and then only change one entry. And so the last insight is, let's deviate slightly from this strict notion of a DFA and instead do something that works better with this notion that we just keep a previous state. And the solution for this, if you want to keep drawing like the nice images like this, is a failure link. So these are not automata in a normal sense. Instead, they have normal edges where you have to follow a character if you can read it. But they also have these error links, which if you cannot follow a normal match edge, you have to take the error link, but you don't consume the character. So if you're in state 5 and you read something that's not a C, say you read an A, then you would go via this error edge to state 3 and try again reading the same A. And in this case, again, you cannot really read the A, so you have to do another edge following the error edge again. And you still try to read the same A, and it still doesn't work, so you still have to go the error edge one more step. And in state 0, you finally can read your character A. That's different from our automata as we've seen them before. But this has the benefit that every state needs just a single error edge, a failure link. Now, it's worth to point out the distinction to a non-deterministic finite automaton, because the computation is still deterministic. You have exactly one choice what to do, but you're not always using a character. If you've seen automata before, there's a notion of an epsilon transition in NFAs, where you're allowed to take a transition without reading a character. But these are different. In this case, you either have to take the matching edge, or you have to take the failure link. There's never any ambiguity of what to do. And here's for our famous example from before, ABABACA, the failure link version. And let's first see how we use that to read through the text. But let me do this quickly, because it's similar to what we've done. We start in state 0. We read an A as the next character. Oh, we can do that. Perfect. Then we're done. Then we read a B in that state. Oh, OK, that also works. So we go to state 2. From 2, we read an A. That's the next character in the text. So we go to state 3. From state 3, a B brings us to state 4. 4A takes us to 5. But now from 5, there's no way to read the B. So instead, we go back to 3. And for 3, we can read a B. So here it brings us to state 4. And so on and so forth, OK? Here's that drawn nicely. And it can happen that in a certain state, you have to follow failure links a few times before you can eventually read that character. That's just how these automata work. OK. Wake up time. After a long bit of just listening. it's not a trick question, but it's a question that needs little second thought maybe. Wait for a few more people. All right. Let's see some spread of answers. And the majority got it, but it's a big spread. Now this is asking about the worst case. What's the worst case time to read a single character if we're using such an automaton? And the worst case, as also often, is realized if you have a very boring pattern. Say it's just A's, another one. I mean, you have to take my word for this, but you will find that the failure links always just go back one step in this case. And so if you're sitting in this state, say, and you read a B, then you'll have to bump down essentially m steps before you can read your B. The start state will always have all characters apart from the one that leads there will loop in state 0. That's why in the worst case it takes so much time. Now, apart from just waking you up, that's also pointing out a potential problem, right? We loved our string matching automata because they gave constant time per character in the text as the matching time. And now it seems like we messed this up. Now it could take essentially m time for each character in the text. So that sounds like we're back to n times m. Now, fortunately, that's not true. And the reason in this example, maybe you can see why it can't be true. You can't always have to fall back all the way down the automaton. To be able to have this long path of an expensive character to read, you have to somehow make your way to the right first. And so whenever you have these long chains of expensive reads that don't make progress, you had many cheap ones before. We'll come back to that in a second. I didn't show you full code for the string matching automata, partly because nobody really uses those. There's only fringe use cases, whereas KMP is an algorithm that's a bit more widely used. In practice, sometimes Boyer beats it, so that's the second one we'll come to, but I'm jumping ahead of myself. For KMP, I wanted to give you full code, and so here it is. There's a first part that we haven't talked about yet. That'll be the next slide. We have to compute the failure links, similar to how we computed the automaton before. And the rest of the code explains the matching step. And I'll run through it very quickly because it's what we've seen in the example. We maintain a position in the text and the current state in this automaton, the KMP automaton with failure links. We go through all positions in the text one by one. Then we check if we can take the match edge. If so, we advance to the next state. So we make Q1 bigger and we go to the next symbol in the text. If that by we reach the end of the pattern, we found our match, and we can return that. And remember, we only find out once we've read the entire pattern, so we have to subtract the length of the pattern again to get the starting position. String matching was supposed to return the index of the first character of the match, somewhat arbitrarily. Otherwise, so if we can't take the match edge, we have to follow failure links until we can. And so unless we're already in state 0, we update our state to the failure link, jumping back to the left. And so we do this, and then we go back to the while loop. So we just start trying in the new state again. OK. In terms of space, we only look like we don't really represent the automaton anymore at all. I could draw this picture, but there's only two types of edges, those that are match edges, and I can compute those from the pattern on the fly, or the failure links, and that's a single number for each state. So that's just one array. That's why we just have this. And let's quickly analyze this, because the question pointed out some of the characters in the text might need m time to read them. Potentially dangerous, but fortunately it's not a problem. There's two cases of what can happen. So we'll bound the overall number of iterations of this while loop, because inside, if you look at what happens, there's a few if, then else, and so on, but there's no further loops. So the whole inner loop part from here to here, I wanted that in black. That's all just constant time. We're not doing anything more costly in there. So the only thing that counts is how often do we have this outer repetition of the loop. And so there's these two options. We can either make progress in the text, which means I gets closer to n, which eventually means we're running out of characters in the text. And that happens here and here. Or we shift the pattern forward, and that's a little more subtle. It doesn't necessarily move I, right? It could keep I where it is. But we still shift the pattern forward whenever we update Q. So we have either steps that increase I or steps that increase I minus Q. OK. And in this case, we use that fail is always strictly less than its argument. So when we're in this case, we make Q strictly smaller, and that makes I minus Q strictly bigger. So in total, we can have at most n of these steps where I gets bigger. I never gets smaller, and it starts at 0, and it is at most n. So we can have at most n steps like this. And similarly, this term I minus Q, it starts at 0. It goes up to essentially at most n, and it's incremented by at least 1 whenever we have the green part. So we can have at most n steps of this as well. So in total, we're doing at most 2n symbol comparisons, where the comparison that we pay for is always at this step. OK? That's the trick in this case. You can't analyze the loop in isolation, but there's these two different paths it can take. And both of these each can only happen n times. So in total, there can only be 2n of them at most. What's missing is computing the failure links. And for that, we'll do something very, very analogous to the DFA construction. And indeed, it turns out we've already done everything back then that we needed. It's just that instead of copying columns, we just remember that state X. That failure state that we went to, where we took the column and copied it, that's exactly the state, the target of the failure link. So here's the code for that spelled out. We start initially with setting the failure link to 0. Failure state is also 0. We don't have to do the match edge, so we skip that part. We just set the next entry to X, and then we update X, which means we now have to use the failure link automaton to update X to the next step. So if X is currently 3, then we have to set it to where it was if we read a B. And so while the next character that we see is not the next character we have to read, we again follow a failure link. This -1 is just because we update X, increment X here anyways. So that's a boundary case for the 0. It's the very same idea as we did in more detail for the DFA construction. Now again, we want this to be efficient. And now we have two nested loops. We have an outer loop that runs m times, and we have an inner loop that could potentially run m times. So it could be, if you just look at this, maybe it could be quadratic in m. But it turns out it's not actually like that, with a very similar argument as before. The outer loop is at most m times. But then the inner loop always makes X at least 1 smaller. Remember, fail of X is strictly less than X. So X becomes 1 smaller here, but it's only incremented once here. So every iteration of the inner loop makes X 1 smaller, but it can't go below 0, and it's only incremented by 1 for each iteration of the outer loop. So that means the inner loop has at most m iterations in total, because X starts at 0, it can never go beyond m, and each of these iterations of the inner loop consumes 1 from X. So you have m iterations of the inner loop, m iterations of the outer loop, and 2m simple comparisons, again, from this part at most. If you find this looks very similar to the code before, then wait for the tutorial where you will explore the similarity between those two algorithms, between this one for using the failure link automaton for string matching, and this one for computing the failure links. They're indeed intimately related. For the overall string matching, we have to do both. We first have to compute the failure links. That takes 2m character comparisons at most. And then we have to do the simulation of the automaton reading the text. That's at most 2n character comparisons. So in total, we have time dominated by n plus m, big O of n plus m time. And that for the first time is essentially the best possible time. Because if we were supposed to find all occurrences of the pattern in the text, we at least have to be allowed to read the pattern and the text once. And that already gives you that time. So Knuth Morris Pratt, the algorithm has optimal worst case complexity, which also means the other complexities are sandwiched between the lower bound in the worst case and this. And the space usage is at least reduced to what we need to store the pattern. That's also hard to imagine how you can do much better. Let's have a look and how much you digested this, either from now or from something before this. This is supposed to be more of a question to reflect on what we talked about, and you have all the information you need for answering this. So I'll give you a minute or two to think about it. Can we get to 90? We started out with 128. So we got to 90. Does that mean I should reveal the answers now? Okay, maybe we can get 100. Well, I'll slowly start. 3, 2, and we have 100. 1. Goodie. So there's some controversial answers, and let me discuss a bit what I had in mind here. Some parts of this question may be a bit vague, so don't get too frustrated if what you voted doesn't match my my marking here. The first part, faster pre-processing on the pattern. I think that's a pretty clear one because the DFA had this factor sigma. Unless sigma is really small, the pre-processing on the pattern goes down from m times sigma to essentially big O of m. And that will almost always be faster, even if sigma is not enormous. The matching part, once I've built the automaton or the virtual realization of the automaton in the KMP algorithm, the matching itself is probably faster with the DFA. Maybe something one can discuss, but by and large, it's faster because it doesn't have this factor 2. KMP had overall order n plus m time complexity, and this 2m as an upper bound of the symbol comparisons, but the string matching automaton has basically a factor 1. It uses table lookup, not comparisons, but it will be similar in time. So actually, the string matching automaton wins on this part, but it's bought with much more space. So KMP uses less space because we're losing the factor sigma. That was the whole point that I mentioned at the beginning. And that also means it makes the running time independent of sigma, which is maybe somewhat surprising, right? It doesn't matter how many different characters there are in the pattern or the text. Maybe that sounds dubious at first, but remember, all we're doing is symbol comparisons. So as long as it takes constant time to take two characters and tell you are they equal or not, it's actually no contradiction here. I skip this one. Fewer character comparisons. That's a bit of a cheat because the string matching automaton doesn't really use character comparisons. Yeah. You could also say accesses to the characters the string matching automaton probably still wins, at least for the matching part, because it accesses each text character at most once. The KMP algorithm might have to access the same character several times, at most 2 on average, but is a factor 2 again. Right. And okay, whatever. Depends on your liking. One last part that belongs into the KMP section is a remark that this prefix function, the failure links, this fail array, where is it here, is actually much more versatile than just doing what we've done, string matching with it. In a sense, it seems to capture some self-similarity in the pattern that was found to be useful in many other contexts. And that also means that people gave it slightly different names and slightly different conventions before it was formalized in this version. And so if you read about this in other books, it can be a bit confusing because they use slightly different notation. So the typical thing you find is the KMP prefix function or Knuth's prefix function, or slightly different names for that, often denoted as F. And you can remember that F is essentially the same as fail. It's just a shift by 1 in the index. So the definition that people would give for the prefix function is f of j is the length of the longest prefix of the prefix of the pattern ending at index j. That is also a suffix of that thing if you chop off the first character. So again, in pictures, here's our entire pattern. Here's position 0 up to j. So f of j is the length of the longest prefix. So we have some shifted version of this. That's p again, shifted. The length of the longest prefix that matches here. And I guess mismatches after, and there's no shorter way. So that is f of j. Right, and that's very similar to how we defined the string matching transitions. So there's no surprise that this is the same as fail, apart from renaming things. So the difference for us, fail of j would have been excluding that position j. Otherwise, it's the same. So that also means it's useful to memorize this alternative definition of the failure links. Fail of j is the length of the longest prefix of the first j characters of the pattern. That is also a suffix of that thing if we chop off the first character. And again, the prefix suffix thing is just a convoluted way to say what the picture says. This whole thing is a prefix of the pattern. Now we take another prefix of the pattern, and it should be a suffix of that prefix. Untangling the words in pictures usually makes it easier. But it's probably good to memorize this and untangle it when you need it on the spot. So this will crop up in other efficient string algorithms, often under the name of prefix function, so I wanted you to know about it.